as we all are familiar with the semiconductor fabrication, we are used to building large wafers, and these wafers are typically, they have two things. One is the transistor, and the other are the wires. And based off of that, we do all the design work. So, and then we have these substrates that are the interconnects. And on top of that, we take that piece of silicon and put that on and create a chip. That's what we are familiar with today. So things have changed a little bit in the last few years. And what you are looking at, the cross-section here, is the most popular Blackwell chip from NVIDIA that's shipping in the market. Okay, so it's built with two dies that are identical to each other, and they are placed on a pretty interesting interposer technology and combined with high bandwidth memory. I'll come back to this slide in a minute. Okay, so if you look at the semiconductor landscape today, you will hear a lot of these acronyms like gate-all-around, FinFET, planar. And on the packaging side, the buzzword is CoWoS, chip on wafer on substrate. And then there are some panel level fan-out technologies that are also coming up. And if you look at all of this manufacturing capability, the most interesting component where we can get a lot of margin business is the AI processor and the AI application. But at the same time, we have applications for networking, crypto mining, ASICs, and then radio frequency, automotive, edge devices, all of those cell phones that you have in your pocket are using all of these technologies. But AI today is the main driver for the chiplets. Okay, so if you look at the AI market today, what meets the eye is we have the APIs and people are selling tokens per dollar, and then we have large language models and small language models. That's what people think of AI. And that's what's driving the business. But the reality is there's a lot of hardware underneath. And I listed out where chiplet activity is going on in various areas. So obviously all the networking that goes into the data center and across the rack, that means ASICs and chips of various sorts. You need I/O chiplets, you need network on chip type of components, SRAM, co-packaged optics, high bandwidth memory, DDR, GPU, CPU, SRAM, and the most interesting one these days are vertical power delivery, so vertical voltage regulators and passive integrated devices. So there's one thing that I'd like to point out. Last year, same time, we were talking about the picture on the left side, which is the air-cooled system based on a OCP open accelerator infrastructure platform. And this was the talk of the town. Today, the one on the right-hand side is the NVL72 from NVIDIA, which is also based on OCP MGX format. That is the machine to run everything on, because that machine on the right-hand side can handle the full trillion parameter model, which is the LLM. So you can literally buy a box for $4 million and pretty much run the whole ChatGPT like thing on it. But it's more expensive, and the engineering is a lot more intense. Okay, so the air-cooled ones were about 50 kilowatt. Now you will hear 120 kilowatt is what's shipping, and a megawatt rack is on the horizon. Okay, so there is just that much demand in the market right now for these machines to run all of that AI infrastructure. Okay, so if I take the trays out of these boxes, you will see the air-cooled one is somewhere around 4 to 8 rack units. Whereas if you look at the liquid cooled one, it's just one pizza box fix, one rack unit, maybe there is a 2 rack unit version of it. So that has implications on how do we design all of these chiplets. So if you look at the one on the right-hand side, you will see there are those 2 green plates that were referred to as super chips, but it's a combination of 2 GPUs and 1 CPU. So the key trend the change that we are seeing at the moment compared to last year is the focus on how do we make liquid cooled systems and put in a lot more power than we were able to do last time. That means a lot of engineering opportunity, a lot of designing for mechanical engineering, not just electrical engineers. So this is pretty awesome. I had never thought I'd see a chip run about maybe 400 watts in my lifetime, but now we're talking about measuring in horsepower, right, as opposed to watts. So there are 2 key chiplet integration design styles that I want to introduce to you. One is the in-house chiplets, and the other is the concept of chiplet chassis, which is emerging at the moment. So what you have on the screen is basically a rendition of MI300 and Grace Blackwell 200 system. These are all in-house chiplets. Very intense engineering, a lot of investment to bring these things up, and it just resides within few companies that can afford to build these systems. And with the help of OCP, we are trying to open things up, and things are going in the right direction. So coming back to Grace Blackwell that I was showing you before, if you look at the system, what the company did, they built one chiplet, and they put piece 2 of those together and design all the packaging to go with it. Now imagine tomorrow they may have those 3 chiplets or a 4 chiplet version, right? So it's very clever that with one chiplet they can create many variants. Okay, so key enabling technology for packaging appears to be what's called CoWoS-L. It's basically a bridge technology where there is a little piece of silicon that provides really high density interconnect where it's needed. And the rest is primarily the mechanical support and provides power. So last year with MI300, this was the other design style where AMD spent a lot of engineering. They built 5 different chiplets. They created a platform, and they have CPUs, GPUs, base die. The whole infrastructure was developed there. And during last 12 months, I think they have shipped maybe 2 or 3 different variations of it already. And I wouldn't be surprised that they will be able to increase to more. Now comes the new thing that is 2 months old. And here, a number of companies are now offering a harness, a chiplet chassis. That was actually the thing that I was trying to do 10 years ago with ZBlue. So, but now is the time where the backend companies are investing in building the interposers and substrates and base dies. And what happens is you can basically amortize the cost of this across various customers. And you will see this is based on some industry reports that a product similar to this one might be on the horizon, where that XPU is designed by a company that basically understands their software and how to accelerate it, and just plugs it into this harness. So now we are beginning to see the concept of chiplet sockets. It's not the actual physical, but it's kind of like the logical way to put that on. So chiplet ecosystems are emerging. And 10 years ago, when I was starting, this whole thing was empty. And now this chart is horribly incomplete. Okay, the amount of business that is going through in some of these applications is just pretty amazing. I'll say a few words about some of the design solutions. So just think back about MI300 that I was telling you about, and you are the engineering manager to do that design. You have to run 5 or 6 different teams in parallel. You have to make sure that all of that execution is all aligned. It's a lot of work. Okay, so typically in the design process, we think about the architecture that we're gonna pick. We think about the technology selection, die-to-die interfaces, and the design execution. Okay, so this is one important slide, and this is not 100% correct because there are companies that are trying to do it differently, but today we start typically with this decision, are we going to use high bandwidth memory in the system? If we are, most likely we are going in the direction of advanced packaging. And from there on, we decide, do we want to do all the design in-house or do we work with a backend supplier? There is potential in maybe enabling something without advanced packaging, but you will most likely be taking some kind of performance hit. But we are looking for anybody might be able to disrupt this with new architecture will be awesome. So the key things in the design are how to do meet the performance, how to do the partitioning of the design, how to handle thermal and power at a very early stage, and be able to do the connections. That's the routing feasibility. Okay, so you will hear in this conference a lot about die-to-die interfaces and their standardization. None of the products in the market today are using standard interfaces. Everybody has their own. Okay, so, but with the help of OCP and others, we've been on a mission to standardize and build the open marketplace by pushing standards like BOW and UCIe. And then from there on, the new concepts of defining chiplet chassis and the sockets, they are emerging at the moment, and they're very promising. So I'm going to close this section with one thought, which is imagine if you don't have to do all of that engineering of 5 chiplets in-house, and you basically work with some kind of a foundational design, and that basically helps you manage the cost. So let's go back to the NVL72 and think about this particular design. One compute node has 8 GPUs, 2 CPUs, 32 HBM, 4 interposers, and 6 substrates. Okay, now this is where we think we are going into the future. Okay, which is a lot of chiplets can be crammed into this one box, and there's a reason for it. Even within the rack, there are 5,000 wires going up and down. So if you can bring all of that on one board, last time the claim was that they saved 30% energy just by going to liquid cooling. So maybe another 30% can be saved by something like this, but this technology doesn't exist. Okay, so this needs to be developed. And I'm zooming in on this one. If you look at that one, it's basically these large wafer scale interposers made of silicon. And you are seeing about 5 of them on that board that fits the same real estate. And there are chiplets that basically plug into sockets that come from a library. So imagine that if all of this is available, what kind of systems will you be able to build? And because brute force computing methodology of AI today is based on just a lot of computation. This helps. Okay, so and then you can go to the next level. I'm going to leave you with one thought and with one call to action, which is kind of critical, and we have been talking in this conference about that. Primarily, what to do about compute power reduction. Okay, so on the chart on the left side, are different power reduction techniques that we have deployed in last 2-3 decades, but we are really stuck on one of them, and that is the voltage of operation. So 10 years ago, there was a lot of discussion of, okay, let's optimize software for domain specific, and then let's build hardware that is domain specific. A lot of that is happening already. But what's not happening, the voltage of operation is kind of like stuck. Yeah, sometimes we can maybe operate it at 0.6 volts, but nominally it's about 1 volt. We just really can't go below that. And the other thing to think is 1,000-watt chip and 1 volt, you have 1,000 amperes. Handling that 1,000 amperes is just not easy, right? So this is the opportunity. Go after the transistor VDD, not the nanometers. I think nanometer is a great idea, but I think it's run out of steam. So whoever solves the VDD problem, I think a technology like this will be of great importance and interest.